Okay, so this is a continuation of our last problem. So they say they want us to graph the derivative of y equals x cubed and examine the intervals. So the derivative, remember, was 3x squared. So we know that this is going to be a quadratic or a parabola that has been vertically stretched by a factor of 3. So you can see, I'm just going to label A here, B here, C here. Our derivative, or this graph, is decreasing or going down from point A to B. This means that the function is going to be concave down. Now, if I think about tangent lines here, all of these tangent lines are going to be negative. So if the tangents are negative, then that means our second derivative is going to be negative as well. Now the exact opposite thing is happening to the right of 0. So when I look from point B to point C, this graph is increasing or going up, and this means that it is concave up. Now again, the exact opposite thing happens. Our tangents are positive, and that means that our second derivative is going to be greater than 0. So just to summarize, when f double prime of x, or when our second derivative is equal to 0, that means that we have a point of inflection. All right, our third and final example. Sketch the function f of x equals 5x cubed minus x to the power of 5 by finding the intercepts, critical points, and all points of inflection. So I'm going to go ahead and just start this off with my intercepts. And again, it doesn't matter what order you do this in. I'm just going to do the y first. So I'm going to go ahead and set x equal to 0. So I have y is equal to 5 times 0 cubed minus 0 to the 5, which is 0. So I know that my y-intercept is at 0, 0. Now, x-intercepts, I'm going to let y equal 0, so I'm going to get 0 is equal to 5x cubed minus x to the 5. This is going to be nice and easy for us to factor. I will take out an x cubed, and I'll be left with 5 minus x squared. This is going to leave me with an x-intercept of 0, which makes sense since our y-intercept was the origin. And then this is going to leave me with 2 x-intercepts. So one of them is going to be root 5, and the other is going to be negative root 5. So this means that I have the points 0, 0, root 5, 0, and negative root 5, 0. Now, one thing I did want to mention, since we are going to be plotting these, or on our sketch eventually, you can go ahead and change these to decimals right now. So we have one at 2.2 and one at negative 2.2. The next thing that we're going to do is solve for our critical points. So remembering that is when we do the derivative and set that equal to 0. So my derivative is going to equal 15x squared minus 5x to the power of 4. When I set that equal to 0, I can go ahead and factor a little bit of this right now. 5x squared, I'll be left with 3 minus x squared. And so what this is leaving me with is a critical point at 0, and then 2 more critical points. One of them is going to be at x equals root 3, and the other one at negative root 3. Now, getting the actual coordinate on our sketch isn't as easy with critical points as it was when we were finding our intercepts. So what we need to do is we need to actually take these x values and plug those back into the original function to find out what the corresponding y values are. So 0 is easy. We already know that that's 0, 0. We've seen it pop up in the x-intercepts and y-intercepts. The root 3 isn't so easy. So if I go ahead and I plug that into my original function, so I do f of root 3, I'm going to get 6 root 3 And then if I plug in negative root 3, I am going to get negative 6 root 3. So these are 3 more points that are on our original function. At this point in time, I can go ahead and change these into decimals as well. Remember, we're going to be plotting them. It's not so easy to plot 6 root 3, so we can go ahead and change those to decimals. So 1.7 and approximately 10.4, and a negative 1.7 and a negative 10.4. All right, so I have this interval chart done here. I've included all of our critical points. So we have one at negative root 3. We know that when we plug that into our derivative, it's 0, one at 0, and one at root 3. So those ones are easy. I'm going to go ahead and I'm going to pick a test value and I'm going to plug that into our derivative to see what happens. So for something less than negative root 3, I'm going to choose a test value of negative 2. And if I plug that into my derivative function, I am going to get a negative result. I'm going to do the exact same thing here. I will choose... Sorry about that. I had someone knocking on my door. I'm going to choose a test value of negative 1. And when I plug that into my derivative, I get a positive result. Something between 0 and root 3, I will choose that test value of 1. And I'm going to get a positive result. And then when I have to do something bigger than root 3, again, I will choose a test value of positive 2. And I will get a negative result. So what this means when I think about my original function is that since the derivative, I got a negative result, this would be decreasing. We know that at a 0, it's always going to be horizontal. Since this is positive, we're increasing again, and then we're decreasing. So if we think about what's happening here, we're decreasing, followed by a horizontal, followed by an increase. So we can very clearly see that this is going to represent a minimum. On the next interval, I'll use a different color here, we're increasing with a horizontal with an increase. Now we know that that means that we should be getting a point of inflection here. And then I will use a different color again. We have an increase with a horizontal with a decrease. So this is going to represent a maximum. The last thing that we had to find was the points of inflection. So remember, the points of inflection occur when the double derivative is set equal to 0. So just so we remember it, I rewrote the derivative here for us. This means that our double derivative is going to be 30x minus 20x cubed. And then I'm going to go ahead and set that equal to 0. Now at this point, I can go ahead and factor. So I will pull out a 10x, and I'm going to be left with 3 minus 2x squared, and this means that I'm going to have an x of 0, and 3 is equal to 2x squared, which leaves me with x is equal to plus or minus the square root of 3 over 2. Now again, because we are going to be sketching these, I am just going to rewrite these in decimals. So what we have here is we have a positive root 3 over 2, which is going to be approximately 1.2. And when I plug this 1.2 into my original function, into my f of x, and you can go ahead and double check this with your calculator, you should get approximately 6.4. And then I'm going to do the exact same thing for the negative root 3 over 2, and I'm going to be getting a negative 6.4. Alright, so we're creating our second interval chart here. This one is to check for our concavity. So I've went ahead and I've plugged these points of inflection in, the points that we just solved for. And so I know that at negative root 3 over 2, this root should go over the whole thing, and at 0 and at positive root 3 over 2, the double derivative is equal to 0 when I plug those in. I'm going to go ahead and choose some test values. So I will choose a test value of negative 2 again, and when I plug that into my double derivative, I'm going to get a positive result. something between negative root 3 over 2 and 0, I'm going to choose a test value of negative 1. And when I plug that in, it will be a negative result. Something between 0 and root 3 over 2, I will choose a test value of 1. And when I plug that into my double derivative, I'm getting a positive result. And then here I'm going to choose a test value of 2, and I will get a negative result. And so what this means in terms of our original function is that I'm getting something that's concave up. Here we clearly know that we have a point of inflection. Since this double derivative is a negative result, this would mean concave down. Our next point of inflection, concave up. Our final point of inflection, and then another concave down. So we do not always get all of our points of inflection when we find our critical points, so it is very important that we do this second derivative and set it equal to 0 and do this concavity interval chart so we can see exactly what's going on. At this time, we do have all of the information that we need to do our sketch, so we'll get started on that right now. So just to remind you, our original function was 5x cubed minus x to the 5. I'm just going to go through, and I should have done it at the beginning and I didn't, but what we know about this function is that it is a degree 5. I know that it has a negative leading coefficient, so if I look right there, I can see that that's negative. And so what this means is that if I have a degree 5, which is an odd function with a negative leading coefficient, it's going to be going from quadrant 2 to quadrant 4. Alright, so you can see that I have put a sketch right from Desmos in here, or a graph right from Desmos in here. I have included some of our important points. So I've put in all 3 of our x-intercepts. Our x-intercept was the exact same as the y-intercept. And then I also put in those critical points. So this local min, this local max, and that 0, 0, that point of inflection that we found. So what I wanted to show you is that this point of inflection is very obvious. We can see that it's increasing the entire time, but we can very easily see where it changes from concave down to concave up. It's not always going to look so obvious on our graph. If I add in the 2 other points of inflection that we found, we have one at negative 1.2 and then negative 6.4, and then we have another at 1.2 and 6.4. It's a little bit more obvious. Sorry, let me see here. There we go. You can kind of see that at this point we have it changing from a concave up to a concave down. And then at this point, the 1.2, 6.4, we are going concave up to concave down.